Chapter 6. Flight Maneuvers. Introduction. Flying a weight shift control, WSC. Aircraft is not like driving an automobile on the highway. It is also different from operating the controls of an airplane. A WSC pilot holds the control bar, which is a structural component of the wing, in his or her hands. This wing is attached to the carriage and freely rotates laterally and longitudinally about the hang point. Therefore, the feel of the WSC is completely different from other aircraft because there are no movable control surfaces actuated through push/pull rods or cables connected to a separate control actuator, such as a stick or yoke. The pilot feels forces on the wing through the control bar, which is part of the wing structure with no mechanical advantage. Simply, the feel of the WSC is different from other aircraft, but the basic flight maneuvers are similar. End of page 6-1. Practicing the basics with precision and understanding the effects on the pilot and the aircraft develop a feel for the aircraft in flight so the pilot can concentrate on the flying mission at hand and not on the mechanical movements. The ability to perform any assigned maneuver is only a matter of obtaining a clear visual and mental conception of it so that perfect performance is a habit without conscious effort. Begin with the flight basics to build a foundation for precision flying. Takeoffs/landings and emergency maneuvers are covered in later chapters. All flying tasks are based on the four fundamental flight maneuvers. 1. Straight and level flight. 2. Turns. 3. Climbs. For a descent-controlled flight consists of either one or a combination of these basic maneuvers. Effects and the use of the controls. In using the flight controls, the results should be looked at in relation to the pilot. The pilot should always be considered the center of movement of the aircraft or the reference point from which the movements are judged and described. The important concept and a foundation for all flight maneuvers is not to think of the controls in terms of up or down in respect to the earth. This is only a relative state to the pilot. Controls need to be thought of in relation to the pilot, so that the control use can be for any flight attitude, whether climbing, diving, banking, or a combination of these. Sideways pressure applied by moving the control bar to the left lowers the right wing in relation to the pilot. Moving the control bar to the right lowers the left wing in relation to the pilot. This is roll control as discussed in Chapter 2, Aerodynamics. Figure 6.1. Pushing and forward pressure applied to the control bar results in the WSC aircraft's nose rising in relation to the pilot slowing down the WSC, while pulling in or back pressure results in the nose lowering in relation to the pilot increasing speed of the WSC. At the same trim speed, increasing the throttle results in the nose remaining at the same level in relation to the pilot but raising pitch with increased throttle and lowering pitch with decreased throttle in relation to the Earth's horizon. Both control bar and throttle affect pitch in relation to the Earth's horizon. This is pitch control, as discussed in Chapter 2, Aerodynamics. Figure 6.2. End of page 6-2. Feel of the aircraft. All WSC aircraft controls have a natural live pressure while in flight and will remain in a neutral position of their own accord if the aircraft is trimmed properly. The pilot should think of exerting a force on the controls against this live pressure or resistance. It is the duration and amount of force exerted on the control bar that affects the controls and maneuvers the WSC aircraft. The actual amount of the control input is of little importance, but it is important that the pilot maneuver the aircraft by applying sufficient control pressure to obtain a desired result, regardless of how far the control bar is actually moved. The controls should be held lightly, not grabbed and squeezed. A common error for beginning pilots is a tendency to tightly grip the bar. This tendency should be avoided as it prevents the development of feel, which is an important part of aircraft control. Figure 6.3. However, for WSC aircraft, the controls do need to be gripped during moderate and severe turbulence to make sure the wing does not get ripped out of the pilot's hands. This is why flying a WSC aircraft in turbulence requires strength and endurance. It can be fatiguing if the pilot is not used to or in shape for this type of flying. The initial flight training should be done in calm conditions so the student can use a soft touch on the controls to develop the feel for the WSC aircraft. The ability to sense a flight condition is often called feel of the aircraft, but senses in addition to feel are also involved. Sounds inherent to flight are an important sense in developing feel. The air that rushes past an open flight deck can be felt and heard easily within the tolerances of the Practical Test Standards, PTS, of plus or minus 10 knots. When the level of sound increases, it indicates that airspeed is increasing. In addition to the sound of the air rushing past is also felt unless an effective windscreen is placed in front of the pilot blocking the wind. Figure 6.4. The power plant emits distinctive sound patterns in different conditions of flight. The sound of the engine in cruise flight sounds different from the sound in a glide or a climb. Overall, there are 3 sources of actual feel that are very important to the pilot. 1. The first source is the pilot's own body as it responds to forces of acceleration. The G-loads, as discussed in Chapter 2, imposed on the airframe are also felt by the pilot. Centripetal acceleration forces the pilot down into the seat or raises the pilot against the seatbelt. Radial accelerations, although minor for WSC aircraft, are caused by minor slips or skids in uncoordinated flight and shift the pilot from side to side in the seat. These forces are all perceptible and useful to the pilot. Flight time plus the pilot's desire to feel the aircraft provides the pilot an excellent feel for the aircraft and the ability to detect even the smallest change in flight. A goal for any pilot should be to constantly develop a better feel for their aircraft. End of page 6-3. 2. The response of the controls to the pilot's touch is another element of feel, and is one that provides direct information concerning airspeed. 3. Another type of feel comes to the pilot through the airframe. It consists mainly of vibration. An example is the aerodynamic buffeting and shaking that precedes a stall. Different airspeeds and power settings can also provide a subtle feel in aircraft vibrations. Kinesthesia, or the sensing of changes in direction or speed of motion, is one of the most important senses a pilot can develop. When properly developed, kinesthesia can warn the pilot of changes in speed and/or the beginning of a settling or mushing of the aircraft. The senses that contribute to feel of the aircraft are inherent in every person. However, feel must be developed. It is a well-established fact that the pilot who develops a feel for the aircraft early in flight training has little difficulty with advanced flight maneuvers. Attitude flying. Flying by attitude means visually establishing the aircraft's attitude with reference to the natural horizon. Attitude is the angular difference measured between an aircraft's axis and the Earth's horizon. As discussed in Chapter 2, Aerodynamics, pitch attitude is the angle formed by the longitudinal axis, and bank attitude is the angle formed by the lateral axis. Rotation about the aircraft's vertical axis, yaw, is termed an attitude relative to the aircraft's flight path, but not relative to the natural horizon. In attitude flying, aircraft control is composed of 3 components. 1. Bank control, control of the aircraft about the longitudinal axis to attain a desired bank angle in relation to the natural horizon. This can be easily seen in a WSC aircraft by looking at the angle the front tube makes with the horizon. Figure 6.5. 2. Pitch control, control of the aircraft about the lateral axis to raise and lower the nose in relation to the natural horizon. 3. Power control, used when the flight situation indicates a need for a change in thrust, which at a constant speed raises and lowers the nose in relationship to the horizon, similar to pitch control. Straight and level flying. Flying straight and level is the most important flight maneuver to master. It is impossible to emphasize too strongly the necessity for forming correct habits in flying straight and level. End of page 6-4. All flight is in essence a deviation from this fundamental flight maneuver. It is not uncommon to find a pilot whose basic flying ability consistently falls just short of minimum expected standards, and upon analyzing the reasons for the shortcomings discover that the cause is the inability to fly straight and level properly. In learning to control the aircraft in level flight, it is important that the control forces be exerted just enough to produce the desired result. Some wings are more responsive than others. The student should learn to associate the apparent movement of the control bar with the response in pitch and roll. In this way, the student can develop the ability to regulate the change desired in the aircraft's attitude by the amount and direction of forces applied to the controls without the necessity of referring to outside references for each minor correction. Straight and level flight is flight in which a constant heading and altitude are maintained. It is accomplished by making immediate and measured corrections for deviations in direction and altitude from unintentional slight turns, descents, and climbs. Level flight is a matter of consciously fixing the relationship of the position of something on the aircraft, used as a reference point with a point on the horizon. In establishing the reference point on the aircraft, place the aircraft in the desired position and select a reference point. A typical reference point on the WSC aircraft is a point on the front tube. The WSC aircraft reference point depends on where the pilot is sitting, the pilot's height, whether short or tall, and the pilot's manner of sitting. It is, therefore, important when establishing this relationship, the pilot sit in a normal manner, otherwise the points will not be the same when the normal position is resumed. Figures 6, 6 and 6-7. Straight and level flight should first be practiced in calm air where the control movements determine the actual movement through the air, and air movement has minimal effect on the aircraft's altitude and direction. A trim speed needs to be set if the WSC aircraft has an in-flight trim system or the trim speed set on the ground is used. The throttle is adjusted so the aircraft is flying level, not climbing or descending. This can be determined by looking at the altimeter or the vertical speed indicator, if so equipped. The throttle setting is the control for maintaining level flight for a specific weight, loading, trim speed, and density altitude. Level flight is maintained by selecting some portion of the aircraft's nose as a reference point, and then keeping that point in a fixed position relative to the horizon. Using the principles of attitude flying, that position should be cross-checked occasionally against the altimeter to determine whether or not the throttle setting and pitch attitude are correct. If altitude is being gained or lost, the pitch attitude should be readjusted with the throttle in relation to the horizon. Then, recheck the altimeter to determine if altitude is being maintained and adjust the throttle accordingly. The throttle setting for this condition should be noted in all future changes in weight, trim speed, and density altitude reference to this known throttle setting. After level flight is mastered in calm air, it can be practiced in air that is moving, minor turbulence or active air. The throttle settings for similar weight, trim, and density altitude are the same, but more pilot input is required to maintain a constant altitude. The throttle is used to maintain a selected distance above the reference point for local air movement, but the pitch pressure, nose up or nose down, is used to control this attitude for shorter duration air disturbances. Typically, updrafts or thermals raise the nose of the aircraft and downdrafts at the edge of thermals lower the nose of the aircraft. For minor updrafts, the nose is lowered by pitch control input by the pilot slightly increasing the speed of the aircraft to keep the pitch at a constant level. In moderate to severe updrafts, the throttle can be reduced to assist in maintaining a reasonably constant pitch angle with the horizon. Similarly, for minor downdrafts that lower the nose is raised by pitch control input by the pilot slightly decreasing the speed of the aircraft to keep the pitch at a constant level. An additional caution for raising the nose and decreasing the speed is that raising the nose too high could stall the aircraft. Therefore, caution must be exercised in moderate downdrafts not to reduce the speed too much to approach a stall speed/critical angle of attack. Similar to reducing the throttle in updrafts to reduce pitch angle, increasing the throttle typically increases the pitch angle. Figures 6, 8. WSC aircraft can use the front tube as a reference to a line perpendicular with the horizon and the wings leveled. It should be noted that any time the wings are banked even slightly, the aircraft will turn. The front tube can be used as an indicator to determine turn rate. If the bar is moving side to side to any established reference point, the aircraft is banked and should be corrected to eliminate any turn. The objective of straight and level flight is to detect small deviations from level flight as soon as they occur, necessitating only small corrections. Straight and level flight requires almost no application of control pressures if the aircraft is properly trimmed and the air is smooth. End of page 6-5. Figure 6, 6. A reference point on the horizon chosen. Figure 6, 7. Pilot's view of a reference point on the front tube chosen for level flight and lined up with the reference point on the horizon for straight and level flight. End of page 6-6. For that reason, pilots must not form the habit of constant, unnecessary control movement. Pilots should learn to recognize when corrections are necessary, and then make a measured response easily and naturally. Common errors in the performance of straight and level flight are: 1. Attempting to use improper reference points on the aircraft to establish attitude. 2. Forgetting the location of selected reference points. 3. Too tight a grip on the flight controls resulting in over-control and lack of feel. 4. Improper scanning and/or devoting insufficient time to outside visual reference, head in the flight deck. 5. A fixation on the nose, pitch attitude, reference point only. 6. Unnecessary or inappropriate control inputs. 7. Failure to make timely and measured control inputs when deviations from straight and level flight are detected. 8. Inadequate attention to sensory inputs in developing feel for the aircraft. Trim control. The use of trim systems relieves the pilot of the requirement to exert pressures for the desired flight condition. An improperly trimmed aircraft requires constant control pressures, produces. Most WSC aircraft have a ground-adjustable pitch/speed trim system that adjusts the carriage hang point on the wing keel that is set for the desired speed. Some WSC aircraft have additional pitch control systems that can adjust the trim speed in flight as described in Chapter 3, Components and Systems. There is no yaw trim, but the roll trim is usually adjusted on the ground for a wing that has a turn in it. Roll trim is usually adjusted so the wing flies straight in cruise flight. This is a balance between the full power torque of the engine wanting to turn it in one direction and minimum power when the WSC aircraft is in a glide. WSC pilots usually have to exert some pilot roll input for high-power engines at full power climb to fly straight because of the engine turning effect. Level turns. A turn is made by banking the wings in the direction of the desired turn. A specific angle of bank is selected by the pilot, control pressures are applied to achieve the desired bank angle, and appropriate control pressures are exerted to maintain the desired bank angle once it is established. End of page 6 to 7. Banking is performed with the following steps, figure 6, 9. Entering a turn. A. Straight flight. B. A pilot applies sideways pressure to the control bar, shifting the weight towards the direction of the desired turn, initiating the bank. C. Turn is established and maintained by moving the control bar back to the center position. Exiting a turn. D. A pilot is maintaining stabilized bank and a resultant turn. E. Pilot shifts weight to opposite side to initiate exit out of the turn. F. Straight flight is established and maintained by moving the control bar back to the center position. Coordinating the controls. Flight controls are used in close coordination when making level turns. Their functions are: 1. The WSC is banked with side-to-side pressure with the control bar, and the bank angle established determines the rate of turn at any given airspeed. 2. The throttle provides additional thrust used to maintain the WSC in level flight. 3. Pitch control moves the nose of the WSC aircraft up or down in relation to the pilot and perpendicular to the wings. Doing this sets the proper pitch attitude and speed in the turn. Turns are classified to determine the bank angle as follows. 1. Shallow turns are those in which the bank is less than approximately 20 degrees. 2. Medium turns are those resulting from a degree of bank that is approximately 20 degrees to 45 degrees. 3. Steep turns are those resulting from a degree of bank that is 45 degrees or more. Changing the direction of the wings lift toward one side or the other causes the aircraft to be pulled in that direction. When an aircraft is flying straight and level, the total lift is acting perpendicular to the wings and to the earth. Figure 6, 10. As the WSC is banked into a turn, the lift then becomes the resultant of two components. 1. The vertical lift component continues to act perpendicular to the earth and opposes gravity. 2. The horizontal lift component, centripetal, acts parallel to the Earth's surface and opposes inertia, apparent centrifugal force. End of page 6 to 8. These two lift components act at right angles to each other, causing the resultant total lifting force to act perpendicular to the banked wing of the aircraft. It is the horizontal lift component that actually turns the WSC aircraft. Figure 6.10. Shallow turns are accomplished by moving the control bar to the side slightly, waiting for the wing to roll the desired amount, and then releasing the side pressure on the control bar back to the center position. The WSC aircraft will stabilize in the turn with no control pressures required. During a shallow turn, there is no significant increase in airspeed or g-forces that can easily be noticed by the student. Figure 6.11. Once a shallow turn is initiated, it is a good practice to be stabilized at a constant bank and then exit to a predetermined heading. To exit the shallow turn, opposite sideways pressure must be put on the control bar to bring the WSC aircraft back to level flight. For higher bank turns, the entry speed should be well above 1.3 times the stall speed, which increases significantly in higher bank turns. As an example, at least 1.5 times the stall speed should be the entry speed for a 40-degree bank turn to maintain the 1.3 times the stall speed safety margin. Wings with a trim speed of 1.3 times the stall speed require an increase in speed slightly. In all constant altitude, constant airspeed turns, it is necessary to increase the angle of attack of the wing when rolling into the turn by pushing out on the control bar. This is required because part of the vertical lift has been diverted to horizontal lift. Thus, the total lift must be increased to compensate for this loss. Similarly, the throttle must be increased to maintain the same altitude in steeper banks. The additional load or g-force in a medium bank turn is felt as the pilot is pushed down on the seat with enough force for this effect to be noticed. After the bank has been established in a medium turn, all side-to-side roll pressure applied may be relaxed, but forward pressure to maintain a higher angle of attack is still necessary in a steeper bank. The WSC aircraft remains at the selected bank with no further tendency to roll back to level since all the forces are equalized. During the turn, roll, pitch, and throttle controls are adjusted to maintain the desired bank angle, speed, and level altitude. Coordinated flight is the coordination of the three controls to achieve a smooth turn to the desired bank angle while maintaining a constant speed and altitude. The rollout from a turn is similar to the roll-in, except flight controls are applied in the opposite direction. As the angle of bank decreases, the pitch pressure should be relaxed as necessary to maintain speed and the throttle decreased to maintain altitude. Since the aircraft continues turning as long as there is any bank, the rollout must be started before reaching the desired heading. The amount of lead required to roll out of the desired heading depends on the degree of bank used in the turn. Normally, the lead is 1/2 the degrees of bank. For example, if the bank is 30 degrees, lead the rollout by 15 degrees. As the wings become level, the control pressures should be smoothly relaxed so that the controls are neutralized as the aircraft returns to straight and level flight. As the rollout is being completed, attention should be given to outside visual references to determine that the wings are being leveled and the turn stopped. End of page 6 to 9. To understand the relationship between airspeed, bank, and radius of turn, it should be noted that the rate of turn at any given true airspeed depends on the horizontal lift component. The horizontal lift component varies in proportion to the amount of bank. Therefore, the rate of turn at a given true airspeed increases as the angle of bank is increased. On the other hand, when a turn is made at a higher true airspeed at a given bank angle, the inertia is greater and the horizontal lift component required for the turn is greater, causing the turning rate to become slower. Therefore, at a given angle of bank, a higher true airspeed makes the radius of turn larger because the aircraft is turning at a slower rate. Figure 6.12. When changing from a shallow bank to a medium bank, the airspeed of the wing on the outside of the turn increases in relation to the inside wing as the radius of turn decreases. The additional lift developed because of this increase in speed of the wing balances the inherent lateral stability of the aircraft. At any given airspeed, roll pressure is not required to maintain the bank. If the bank is allowed to increase from a medium to a steep bank, the radius of turn decreases further. A steep bank is similar to a medium bank, but all factors increase. Roll and pitch control pressures must increase, throttle must increase further to maintain altitude, and the g-forces increase significantly. Students should build up to steep bank turns gradually after perfecting shallow and medium bank turns. Do not exceed the bank angle limitation in the Pilot's Operating Handbook, POH. The pilot's posture while seated in the aircraft is very important, particularly during turns. It affects the interpretation of outside visual references. Pilots should not lean away from the turn in an attempt to remain upright in relation to the ground rather than ride with the aircraft. This should be a habit developed early so that the pilot can properly learn to use visual references. Beginning students should not use large control applications because this produces a rapid roll rate and allows little time for corrections before the desired bank is reached. Slower, small control displacement roll rates provide more time to make necessary pitch and bank corrections. As soon as the aircraft rolls from the wings level attitude, the nose should also start to move along the horizon, increasing its rate of travel proportionally as the bank is increased. The following variations provide excellent guides. If the nose moves up or down when entering a bank, excessive or insufficient pitch control is being applied. During all turns, the controls are used to correct minor variations as they are in straight and level flight. End of page 6 to 10. Figure 6.12. Angle of airspeed in bank regulate rate and radius of turn. End of page 6 to 11. Instruction in level turns should begin with changing attitude from level to bank, bank to level, and so on with a slight pause at the termination of each phase. This pause allows the WSC to free itself from the effects of any misuse of the controls and ensures a correct start for the next turn. During these exercises, the idea of control forces, rather than movement, should be emphasized by pointing out the resistance of the controls to varying forces applied to them. Common errors in the performance of level turns are: 1. Failure to adequately clear the area before beginning the turn. 2. Attempting to sit up straight, in relation to the ground, during a turn, rather than riding with the aircraft. 3. Failure to maintain a constant bank angle during the turn. 4. Gaining proficiency in turns in only one direction. 5. Failure to coordinate the angle of attack to maintain the proper airspeed. 6. Failure to coordinate the use of throttle to maintain level flight. 7. Altitude gain/loss during the turn. Climbs and climbing turns. When an aircraft enters a climb, it changes its flight path from level flight to an inclined plane or climb attitude. As discussed in Chapter 2, weight in a climb no longer acts in a direction perpendicular to the flight path. It acts in a rearward direction. This causes an increase in total drag, requiring an increase in thrust, power, to balance the forces. An aircraft can only sustain a climb angle when there is sufficient thrust to offset increased drag, therefore, climb is limited by the thrust available. Figure 6.13. Like other maneuvers, climbs should be performed using outside visual references and flight instruments. It is important that the pilot know the engine power settings and pitch attitudes that produce the following conditions of climb. 1. Normal climb, performed at an airspeed recommended by the aircraft manufacturer. Normal climb speed is generally the WSC best rate of climb, VY, speed as discussed below. Faster airspeeds should be used for climbing in turbulent air. 2. Best rate of climb, VY, the airspeed at which an aircraft will gain the greatest amount of altitude in a given unit of time, maximum rate of climb in feet per minute, FPM. The VY made at full allowable power is a maximum climb. This is the most efficient speed because it has the best lift over drag ratio for the aircraft. This speed is also the best glide ratio speed used for going the greatest distance for the amount of altitude, as discussed later in this chapter. Each aircraft manufacturer is different, but a good rule of thumb is that the VY is 1.3 times the stall speed. It must be fully understood that attempts to obtain more climb performance than the aircraft is capable of by increasing pitch attitude results in a decrease in the rate of altitude gain. Trim is usually set at the VY or higher. End of page 6 to 12. 3. Best angle of climb, VX, performed at an airspeed that will produce the most altitude gain in a given horizontal distance. Best VX airspeed is lower than VY but higher than minimum controlled airspeed. The VX results in a steeper climb path, although the aircraft takes longer to reach the same altitude than it would at VY. The VX, therefore, is used in clearing obstacles after takeoff. Since the VX is closer to the stall speed, caution should be exercised using this speed to climb so as not to stall the WSC aircraft close to the ground with potentially catastrophic consequences. Figure 6.14. Climbing flight requires more power than flying level, as described in Chapter 4. When performing a climb, the normal climb speed should be established and the power should be advanced to the climb power recommended by the manufacturer. As the aircraft gains altitude during a climb, the engine has a loss in power because the same volume of air entering the engine's induction system gradually decreases in density as altitude increases. During a climb, a constant heading should be held with the wings level if a straight climb is being performed, or a constant angle of bank and rate of turn if a climbing turn is being performed. To return to straight and level flight, when approaching the target altitude, increase the speed to the cruise setting, if different, and decrease throttle for level flight. After the aircraft is established in level flight at a constant altitude and the desired speed, the aircraft should be trimmed, if equipped with an in-flight trim system. In the performance of climbing turns, the following factors should be considered. 1. With a constant power setting, the same pitch attitude and airspeed cannot be maintained in a bank as in a straight climb due to the increase in the total lift required. 2. The degree of bank should not be too steep. A steep bank significantly decreases the rate of climb. The bank should always remain constant. 3. At a constant power setting and turning while climbing, the WSC aircraft climbs at a slightly shallower climb angle because some of the lift is being used to turn. 4. Attention should be looking at outside references and scanning for traffic with no more than 25% of the time looking at inside flight deck instruments. There are two ways to establish a climbing turn. Either establish a straight climb and then turn, or enter the climb and turn simultaneously. Climbing turns should be used when climbing to the local practice area. Climbing turns allow better visual scanning, and it is easier for other pilots to see a turning aircraft. In any turn, the loss of vertical lift and increased induced drag due to increased angle of attack becomes greater as the angle of bank is increased. So, shallow turns should be used to maintain an efficient rate of climb. All the factors that affect the aircraft during level, constant altitude, turns affected during climbing turns or any other maneuver. End of page 6-13. Common errors in the performance of climbs and climbing turns are: 1. A bank angle too high to achieve an efficient climb. 2. A speed too high to achieve an efficient climb rate. 3. A speed that is too low. 4. Attempting to exceed the aircraft's climb capability. 5. Inability to keep pitch and bank attitude constant during climbing turns. 6. Attempting to establish climb pitch attitude by referencing the airspeed indicator, resulting in chasing the airspeed. Descents and descending turns. When an aircraft enters a descent, it changes its flight path from level to an inclined plane. It is important that the pilot know the power settings and pitch attitudes that produce the following conditions of descent. 1. Partial power descent. The normal method of losing altitude is to descend with partial power. This is often termed cruise or en route descent. The airspeed and power setting recommended by the aircraft manufacturer for prolonged descent should be used. The target descent rate should be 400 to 500 fpm. 2. Steep approach. The normal maneuver used to descend at a steep angle. This is typically used to descend for landing if higher than expected upon approaching the runway. The throttle is set to idle and the airspeed is increased so the excessive drag allows the WSC aircraft to descend at the steepest angle. The control bar is pulled in to achieve this steep approach. The further the bar is pulled in, the steeper the descent rate. Each WSC aircraft is different, but pulling the control bar to the chest may be necessary to achieve the required angle. 3. Descent at minimum safe airspeed. A nose-high descent. This should only be used for unusual situations such as clearing high obstacles for a short runway in an emergency situation. The only advantage is a steeper than normal descent angle. This is similar to the best angle of climb speed and should only be used with caution because stalling near the ground could have catastrophic consequences for the pilot, passenger, and people/property on the ground. 4. Glide. A basic maneuver in which the aircraft loses altitude in a controlled descent with little or no engine power. Forward motion is maintained by gravity pulling the aircraft along an inclined path, and the descent rate is controlled by the pilot balancing the forces of gravity and lift. Figure 6.15. Although glides are directly related to the practice of power-off accuracy landings, they have a specific operational purpose in normal landing approaches and forced landings after engine failure. Therefore, it is necessary that they be performed more subconsciously than other maneuvers because most of the time during their execution, the pilot gives full attention to details other than the mechanics of performing the maneuver. Since glides are usually performed relatively close to the ground, accuracy of their execution, the formation of proper technique, and habits are of special importance. The glide ratio of a WSC aircraft is the distance the aircraft, with power off, travels forward in relation to the altitude it loses. For instance, if it travels 5,000 feet forward while descending 1,000 feet, its glide ratio is said to be 5:1. The glide ratio is affected by all four fundamental forces that act on an aircraft: weight, lift, drag, and thrust. If all factors affecting the aircraft are constant, the glide ratio is constant. End of page 6-14. Although the effective wind is not covered in this section, it is a very prominent force acting on the gliding distance of the aircraft in relationship to its movement over the ground. With a tailwind, the aircraft glides farther because of the higher ground speed. Conversely, with a headwind, the aircraft does not glide as far because of the slower ground speed. Variations in weight for an aircraft with a rigid wing do not affect the glide angle provided the pilot uses the correct airspeed. Since it is the lift over drag (LD) ratio that determines the distance the aircraft can glide, weight does not affect the distance. The glide ratio is based only on the relationship of the aerodynamic forces acting on the aircraft. The only effect weight has is to vary the time the aircraft glides. The heavier the aircraft, the higher the airspeed must be to obtain the same glide ratio. For example, if two aircraft having the same LD ratio but different weights start a glide from the same altitude, the heavier aircraft gliding at a higher airspeed arrives at the same touchdown point in a shorter time. Both aircraft cover the same distance, only the lighter aircraft takes a longer time. However, the WSC aircraft has different characteristics because it has a flexible airframe. As more weight is added to the WSC wing, it flexes more, creating more twist in the wing, decreasing aerodynamic efficiency, as discussed in Chapter 2. For example, a pilot is accustomed to a glide ratio of 5:1 flying solo, a passenger is added, and this glide ratio may decrease to 4:1. This decrease in glide ratio for added weight is true for all descent speeds. The amount of decrease in glide ratio varies significantly between manufacturers and models because each wing flexes differently. The more flexible the wing is, the greater the decrease in glide ratio. Pilots should become familiar with glide ratios for their aircraft at all speeds and all weights. Although the propeller thrust of the aircraft is normally dependent on the power output of the engine, the throttle is in the closed position during a glide, so the thrust is constant. Since power is not used during a glide or power-off approach, the pitch attitude must be adjusted as necessary to maintain a constant airspeed. The best speed for the glide is one at which the aircraft travels the greatest forward distance for a given loss of altitude in still air. This best glide speed corresponds to an angle of attack resulting in the least drag on the aircraft and giving the best lift-to-drag ratio, LDMAX. Figure 6.16. Any change in the gliding airspeed results in a proportionate change in glide ratio. Any speed, other than the best glide speed, results in more drag. Therefore, as the glide airspeed is reduced or increased from the optimum or best glide speed, the glide ratio is also changed. When descending at a speed below the best glide speed, induced drag increases. When descending at a speed above best glide speed, parasite drag increases. In either case, the rate of descent increases and the glide ratio decreases. This leads to a cardinal rule of aircraft flying that a student pilot must understand and appreciate. The pilot must never attempt to stretch a glide by applying nose-up pressure and reducing the airspeed below the aircraft's recommended best glide speed. Attempts to stretch a glide invariably result in an increase in the rate and angle of descent and may precipitate an inadvertent stall. To enter a glide, the pilot should close the throttle and obtain the best glide speed. When the approximate gliding pitch attitude is established, the airspeed indicator should be checked. If the airspeed is higher than the recommended speed, the pitch attitude is too low. If the airspeed is less than recommended, the pitch attitude is too high. Therefore, the pitch attitude should be readjusted accordingly by referencing the horizon. After the adjustment has been made, the the aircraft should be ret-rimmed, if equipped, so that it maintains this attitude without the need to hold pitch pressure on the control bar. The principles of attitude flying require that the proper flight attitude be established using outside visual references first, then using the flight instruments as a secondary check. It is a good practice to always ret-rim the aircraft after each pitch adjustment. End of page 6-15. A stabilized power-off descent at the best glide speed is often referred to as a normal glide. The flight instructor should demonstrate a normal glide and direct the student pilot to memorize the aircraft's angle and speed by visually checking the 1. Aircraft's attitude with reference to the horizon. 2. Noting the pitch of the sound made by the air. 3. Pressure on the controls and the feel of the aircraft. Due to lack of experience, the beginning student may be unable to recognize slight variations of speed and angle of bank immediately by vision or by the pressure required on the controls. The student pilot must use all three elements consciously until they become habits, and must be alert when attention is diverted from the attitude of the aircraft. A student must be responsive to any warning given by a variation in the feel of the aircraft or controls or by a change in the pitch of the sound. After a good comprehension of the normal glide is attained, the student pilot should be instructed of the differences in the results of normal and abnormal glides. Abnormal glides are those conducted at speeds other than the normal best glide speed. Pilots who do not acquire an understanding and appreciation of these differences experience difficulties with accuracy landings, which are comparatively simple if the fundamentals of the glide are thoroughly understood. Gliding turns. Gliding turns have a significant increase in descent rate than straight glides because of the decrease in effective lift due to the direction of the lifting force being at an angle to the pull of gravity. Therefore, it should be clearly understood that the steeper the bank angle, the greater the descent rate. In gliding turns, the decrease in effective lift due to the direction of the lifting force being at an angle to the pull of gravity make it necessary to use more nose-up pressure than is required for a straight glide. However, as discussed earlier, for steeper turns, airspeed must be maintained well above stall speed, which increases during turns where the WSC could stall in the turn. When recovery is being made from a medium or high banked gliding turn, the pitch force which was applied during the turn must be decreased back to trim, which must be coordinated with the roll back to level. In order to maintain the most efficient or normal glide in a turn, more altitude must be sacrificed than in a straight glide, since this is the only way speed can be maintained without power. Attention to the front tube angle with the horizon and the reference point on the front tube provide visual reference of attitudes while gliding. Figures 6-17 and 6-18. Common errors in the performance of descents and descending turns are: 1. Failure to adequately clear the area. 2. Inability to sense changes in airspeed through sound and feel. 3. Failure to maintain constant bank angle during gliding turns. 4. Inadequate nose-up control during glide entry, resulting in too steep a glide. 5. Attempting to establish/maintain a normal glide solely by reference to flight instruments. 6. Attempting to stretch the glide by applying nose-up pressure. 7. Inadequate pitch control during recovery from straight glides. Pitch and power. No discussion of climbs and descents would be complete without touching on the question of what controls altitude and what controls airspeed. The pilot must understand the effects of both power and pitch control, working together, during different conditions of flight. As a general rule, power is used to determine vertical speed and pitch control is used to determine speed. However, there are many variations and combinations to this general statement. Decreasing pitch and diving do provide a quicker descent, but is not typically used as a flight technique for long descents. Changes in pitch through moving the control bar forward and backward are used for maintaining level flight in rising and falling air, and pulling back on the control bar is used for a steep approach technique to lose altitude. However, these techniques are used only for short durations and not the primary altitude control for the WSC. The throttle is the main control used for determining vertical speed. At normal pitch attitudes recommended by the manufacturer and a constant airspeed, the amount of power used determines whether the aircraft climbs, descends, or remains level at that attitude. Steep turn performance maneuver. The objective of the steep turn performance maneuver is to develop the smoothness, coordination, orientation, division of attention, and control techniques necessary for the execution of maximum performance turns when the aircraft is near its performance limits. Smoothness of control use, coordination, and accuracy of execution are the important features of this maneuver. End of page 6-16. Figures 6-17. Pilot's visual reference of pitch and roll descending in a shallow bank. Figure 6-18. Pilot's visual reference of pitch and roll, continuing the shallow bank turn but raising the nose slightly with power application. Notice how the front tube has moved across the horizon and the nose has raised slightly with additional power application to level flight. End of page 6-17.